Bismillah. Distinguished guests, friends, it's great pleasure to welcome you to the first session of second international meeting on frankincense and medicinal plants 2023. Today we have the privilege of hearing from a truly remarkable individual, Professor Dr. Ludger Wisjohan, who is the forefront of natural product chemistry. The undeniable impact on the field is evident through his impressive research record of around 560 publications, more than 16,000 citations, and an H-index of more than 64. Professor Wisjohan is the director of Department of Bioorganic Chemistry, Leibniz Institute of Plant Biochemistry, Germany. Today, Professor Wisjohan will be sharing his expertise on small changes can make large differences, the showcase of Nerium oleander. So without any further delay, please join me in giving a warm and enthusiastic welcome to our keynote speaker, Professor Dr. Ludger Wisjohan.
Thank you for the nice introduction. I don't know, can everybody, not so many, so everybody can probably understand me like it is. I need it, that's perfect. Because that makes it easier.
Okay, yes.
Okay, I changed the title a little bit because we did this Nerium research together with the Dole University, so I introduced it and come show you a little bit what is important. Before I have, my organization demands that to show you this because there's of course some pictures we use which are copyrighted and so on, and there's some unpublished material. So you can film it, but only for your own purpose. You cannot put it in, publish it, or put it into the internet or anything like that. Yeah, only for your own internal stuff. So, how important are small changes? Well, I know here people are not drinking a lot of alcohol, but I tell my students a CH2 group makes all the difference. You won't drink methanol, but you drink ethanol. Okay? And the same is true for the bioactivity of compounds. Very often we think it's a continuum, like we have in medicinal chemistry, and you start from, let's say, a methyl group, and you have ethyl, propyl, and so on, and you have gradual changes. But that's not always the case. Sometimes a little CH2 group or a little change can make all the difference. You need me to use that?
Yes.
Yeah, okay, because of the camera. Yeah, I understand. Okay, so I have brought some examples of these changes which we studied in the past. If you look, for instance, at flavonoids and isoflavonoids, there is this isoflavonoid from isolated, I think, from rice bran or so, and it's used as a phytoestrogenic, so helping women in the menopause to overcome problems. It's very weak. But there is another one from hops, so a beer constituent, but it's a plant by itself. Medicinal plant too, but we take it also in beer in Europe. And that has a very strong phytoestrogenic activity. So it's about 100 of the potency of estrogen, but it's 100 times more than that of the Genesti, which is a marketed product. And you see the only difference between the two is here you have this prenyl group added. Interestingly, if you add a methyl group here, is this a methyl group?
Sorry, can you summarize in a short?
Sorry?
We want to listen.
You just started.
Just start. Okay,
well,
now,
it's the first time.
Okay,
Don't worry.
perfect.
you find it. So I just explained that little changes like this methyl group here means that there is either no activity, or if it's not there, there is a strong activity as a phytoestrogen, for instance. Or similar, tons of preventive properties. If you look at the chart, and we look again here, we have no activity in this compound. We have no activity in this chalcogene compound. But if we have here added a methyl group, we see a strong activity. And another one. Here, without the methyl group, it's no taste. I tried it myself. If you have the methyl group, this is the compound which is it's from hops group, have bitter taste. Okay? So these little changes can not only be a gradual change like we know from medicinal chemistry, it can be really like a yes and no thing. So very important to understand. And very important to then know about what these derivatives do. By the way, the expert on derivatizing phosphoric acids here is Hidayat Hussein, and he is giving a talk, I think, later today. Tomorrow. He's giving a talk. So watch his talk then. Okay. But it's not only true for modifications which are introduced chemically or biochemically, biologically. It's also true for the extraction we do. So here is a few examples of extracts, and which we got from Blue Rashan. Different types of extracts which we tested on gram-positive and gram-negative bacteria from Boswellia samples here. And what you can see is, for the gram-positive, you have some extracts which are not active on gram-negative, but very active on gram-positive. Okay, that's normal, you have them always. The gram-positive is easier. But interestingly, we find one extract, a cold extract, cold aqueous extract, which is more active on gram-negative than it is on gram-positive. That is unusual. Yeah? Of course, as a chemist you say, so what? Of course, if I use different solvents, I extract different compounds. If I use a hot extract, I extract probably more than with a cold extract. We all know flavonoids are soluble in hot water, but not in cold water. That's when your tea gets cold, you get this ring. That is the flavonoids which deposit with a little bit of black dirt around, because they fall out when the tea gets cold. Okay, so nothing of a big surprise. So you get a little bit of quantitative differences, and depending on the solvents, a little bit of qualitative difference. So lipophilic compounds are now dissolved in liquid hexane extract, and so on. So that's so far so normal. But sometimes there is more to it than what meets the standard understanding. And I want to give you the example of the Nerium oleander, very well-known plant, grows everywhere here and in the Mediterranean, very common plant. And the story is that in the Arab literature, the ancient Arab literature, there is some hints how you should do the extracts. And we will come to that later. First of all, what is the important constituent of Nerium? It's so-called cardenolites. Comes from cardia, Greek, heart. So obviously these compounds do something with your heart. Come to that in a second. And what is typical for them is they have this unsaturated lactone, which must be there, and then they have this steroid-like core, and then there may be or may not be several sugars or one sugar or whatever added. I also come to that. Okay. And these things are well known as drugs. So in Germany, we use it from Digitalis, which is another plant. There was also used as arrow poisons in the Mediterranean. Interestingly, Odysseus, famous Greek hero, he used this Helleborus, which flowers, by the way, in winter, very unusual for our region, and not Nerium oleander, although they come from the same region. Well, we don't know why yet, but you will have to see. So what do these cardenolides do? They inhibit, and they can do that at some sites, they inhibit the sodium-potassium pump, which you have in every cell, but especially, of course, in the heart area, it's very important. And then, if you have a little bit of it, you can, of course, enhance the process of, or inhibit this process, and by that have some positive humotropic effect. Only if you have too much, that was it for you, yeah? Not only for your heart, so you're dead. And the problem is that the therapeutic index here is very small. Now, some years ago, we looked into Nerium oleander, which has, of course, these compounds which are cardenolides with certain sugars and certain substitution patterns here, and looked into what they can do in cancer effects. Because, of course, cancer cells also have sodium-potassium channels, and they need them to survive. So the question is, can we make use of it? And old Arabian books suggested that it can be useful without killing the patients or having a lot of heart effects. Now, in the meantime, there was also studies that there is some antiviral effects of this compound, more indirect than directly on the virus, that has to do with the membrane stability and so on. We also see neuroprotective effects studied, and it all has to do with these sodium-potassium ATPase, of course, and I would say more or less in most cases more indirect effects. What is important, though, as said, is the therapeutic index. That means I have different concentrations required for the cardiac activity versus the neuroprotective, antiviral, and anti-cancer activity. Fortunately, this here has the best therapeutic index before I get into some lethal problems. Now, the problem here, as you can see, the cardiac activity versus the toxic one, the lethal one, is just a factor of 10. I mean, nowadays, this would never go to the market. Never, ever. In the past, it did. Yeah? But for traditional, but it was always very dangerous and had to be controlled. The concentration of the ingredients of that had to be controlled very severely. Yeah? And this is still the case. I mean, even if we are with a better margin up here, it still is something which is risky and has to be considered. And therefore, it is very, very important to understand how you make your extract, what it exactly looks like, and how you can produce anything like that in a stable way, because you cannot have it that one day you get an extract where you get a lethal dose from one leaf, and the next extract you need 5 leaves. And this means here the patient is happy, and here it's dead. No option like this, okay? So we really need to understand closely what's happening here. And we need to understand not only from the composition, we need also to understand what's going on in order to have things reproducible. Now, when Rushan came, he came with a story which I considered a little bit spurious, I must admit, because he said me, okay, there is this hot water extract of Nerium which is sold as an anti-cancer drug, but I found, by studying old books and so on, I found that the cold water extract should do much better. He tested it on patients and so on. Now, cold water extract is something you don't like as in a pharmacy or in medicine. Why? Because with the cold water extract, you don't destroy the bacteria, the microorganisms, and so on. Something which you don't want. And it's not so stable either, because the hot water extract or ethanol it automatically stabilizes and sterilizes the sample. Okay, but we had a look at it, and we looked at it more thoroughly, and found that, okay, there is quite some difference. And these differences were not only quantitatively, so you have a little bit more extracted of that and a little bit less of that, as you usually have between hotter and colder extract. It was also not only that you see sometimes in hot extracts you can have hydrolysis enhanced and so on. It was more like that. So I had then some theory developed why a hot extract could be look so different from a cold extract. Do you have any idea why that could be? If it's not the extraction power? Well, my idea behind that was, what does the hot extract do? The hot extract denatures enzymes. The cold extract doesn't denature enzymes. So maybe there is some enzymes in area oleander which you bring together with the compounds when you destroy the tissue, which then make a difference. So we had to prove it. So what would we do? We did a standard methanol extract, which shows us all the compounds, also the more lipophilic one. And we did a cold water and a hot water extract. We did something different. We took a cold water extract, which extracts the compounds with the enzymes active, and then we heated it up afterwards, after the extraction. Then the enzymes are not in there anymore. Do we see a difference? And then later we did something else. We did an enzyme preparation and used it on the hot extract, the one which was not yet treated with enzymes because the enzymes were denatured by the hot water. Okay. And to understand a little bit that it can get quite complicated is that we have several so-called aglycones. So that's the basic triterpenoid core. So we have the oleandric genene. Genene means that it's without the sugar rests, which are usually attached here. So we have the digitoxygenane and so on and so on. With the different core derivatives, and then we have a number of sugars which can be attached to it. And there can be 1, 2, 3, or sometimes even 4 sugars also attached to it. And they make also a big difference in solubility and in activity, as we could show already before in the old paper which we have done with activity and others. So how does that look like? So here you see a total ion chromatogram with the cardiac lipocytes very heavily shown. This is of the cold extract. Now, this is an overlay of the hot extract. Looks totally different. Huh? And here you see the methanol extract, which shows probably all of it. And it shows also that the methanol extract is more close to the hot extract, not to the cold extract, more close to the hot extract. Methanol will do the same. It will denature the enzymes. Okay? That's the theory at this point, or the hypothesis. So can we prove it? Now, the thing we did is we did a metabolic profiling of the whole thing, and then looked into the PCA, the principal component analysis. What it does, it is a mathematical method which scans all the compounds, and it takes out all the compounds which are equal in all samples and concentrates on the differences. The different compounds which show the most differences are shown here. So each spot goes for a compound. And what you can see is you have the hot extract, and it's quite different from the cold extract here. And the cold extract heated up actually is closer to the cold extract than it is to the hot extract. So what does that mean? That means the hot extraction per se is doing the difference, not the temperature as such, because the cold extract then heated up, which would also give them hydrolysis by just heated. It's very similar. Okay, that sounds better. Okay. So here you see it in a different way. It's a bit hard. You can really switch that off. It's not so important to show me. It's better to have a good contrast on the screen, yeah? Otherwise people can't see anything. Okay. So important is the data, not me. It's done by my people anyway, not by me. I'm only presenting for them here, yeah? Okay, thank you. So we have here the hot extract, and the and the cold extract. And what you see in oleandrogenine, this is the aglycone, that you see in the cold extract there's almost nothing. In the hot extract there is something of it, and in the cold extract heated up there is also something, which tells us, okay, this compound is produced because you extract it in the hot extract something which then under heat and water hydrolyzes to give you the genine, which is not so uncommon. I mean, you get hydrolysis away of the sugars here. Now, next point, we looked at the at the oleandrogen diglycoside and the monoglycoside. Okay? So what's happening here? Obviously, in the hot extract, we see the diglycoside, and a lot of it in the methanolic extract, which is a little bit better to dissolve the quite lipophilic or amphiphilic compound. Whereas in the cold extract, we see the monoglycoside, and very little of it in the hot extract. So obviously, in the cold extract, something happened to this compound to form the monoglycoside. Now switch it off, please. Okay. The problem is that the contrast here is too low here then. Okay, then you have just to believe me what I'm saying. Okay. Now, what happens if I take the hot extract, cool it down, and add an enzyme preparation to it? And I get then exactly here hot extract diglycoside, hot extract without enzyme, of course, hot extract plus enzyme. I don't see the diglycosides anymore. It's the same then as with the cold extract. So after all, what we have is the hot extract is destroying the enzymes. By that, it is extracting the original components plus some total hydrolysis, but the cold extract is also extracting this, but the enzyme is active and cleaves it to the monoglycoside. The cold extract also is not strong enough to chemically hydrolyze it to the aglycone. So that makes it very interesting. So here it's put together. Now the interesting fact is now that of course also in the cold extract, and we see a little bit of chemical hydrolysis, and we have of course a worse extraction of the dry and diglycosides. But now with our new method we can of course produce very selectively the monoglycosides even from the hot extract. Yeah. So, overall, to put this part together, why does Nerium do that? Why does it have these enzymes? Very often it's like a chemical. Okay, so sort of prodrug, biological prodrug, if you want to take it. And of course, chemists don't give up, and pharmacologists neither. So effort looked into it, but I come to that later. First, let me tell you our story. He has his own story, so watch it later. Yeah, and also here, Dr. Fiebig. So it's a big team which Professor Rashan collected around this. What we did to understand what mode of action a compound has, which is unknown, we did the following. We take cancer cells and we treat these cancer cells with different, the contrast is very low here, but we treat them with different anti-cancer compounds, and then we look what is the metabolite pattern produced by these compounds. So the cancer cell, when it grows happily, which is bad for us, of course, it produces, let's say we look at 100 compounds and it produces them in a certain concentration each. Now you hit the cancer cell with a drug, which it doesn't like, it disturbs it. So then it produces some compounds less, for instance those which synthesis you inhibit, which gives you then a different pattern of metabolites. Now each cancer drug, depending on which mechanism it goes into, gives you a different pattern. Yeah, because you inhibit different processes in the cell metabolism. And now you can, for cancer drugs for which the metabolism is known, you can correlate them to these patterns of metabolites. And when you do that, that is your training set. So you train your mathematical model with the metabolite patterns for certain mechanisms of action. Then you have the unknown compound. You add it to the cancer cell, and you look at the metabolite pattern, and it tells you, okay, this acts like, let's say, irinotecan anti-cancer drug. So you know it might have the same mechanism. Or you can even identify mechanisms which are combinations of two mechanisms, and so on. So how does this look like? And of course, if nothing fits, you have a new mechanism, which would be fantastic for anyone working in the field, of course. There is not so many. So here you see also this typical principal component analysis of cells which are untreated versus treated. Here, for instance, metformin, it's a complex 1 inhibitor, or with 3-nitrophenol, not nice compounds, not that you'd use them as drugs, but they are really well understood with their modes of action. Or here an HMG-CoA inhibitor, lovastatin, or malonic acid, and you can see how well separated the metabolite groups or patterns are in all these different ones. And when you do that, and we did that with almost 200 something drugs, you can get a tree where you have like a hierarchical cluster of the different drugs and their different mechanisms. So for instance, here the vinca alkaloids, paclitaxel, or here the different complexes, complex 1, 2, 3 from the respiratory chain, and so on. Now, when you find a new one, it can tell you, okay, this new drug has 2 modes of action, or double action, nice, for instance. But you can even go deeper. If you have an untreated control, you see a time dependence because the cells are dying, so metabolism is changing also over time. So it's very important to know that treated after 4 hours and treated after 48 hours and so on has different patterns. So you have to know that. But you can look more closely. If you have, and this is a volcano plot, look into which metabolites are, let's say, up-regulated and which are down-regulated at different times. You can really understand that, for instance, up here, we can see that 6-phosphoglucose, I'm a bit irritated, but this glucose 6-phosphate is upregulated after 4 hours. What's happening? Well, the compound is then likely blocking the way upstream from 6-PG. And we tested that. So you not only understand what is the mode of action, you even can sometimes, not always, pinpoint it to the exact enzyme or the exact receptor which is responsible for the mode of action, without knowing that, without having done any biochemical assay. Of course, this is all correlations. You have then to have a causal proof later. Yeah? But that is very often the problem with all these studies which tell you that frankincense is so good for this and that. Most of them are correlative. Very few are causative. Yeah? That's what we have to work on, of course. But only if you have these causative ones. But this gives you a hint where the cause might be. And then you organize this enzyme and you test the compound directly on it and so on, and then you have your causal proof. Okay. So what happened then with the brestine extract, the cold? Well, when we run it over our system, and you're the first one to see this, well, you see very nicely there is no correlation with all these different, like topoisomerase inhibitors and so on, but with the antimicrotubule activity, which is, of course, not what you learned before with the sodium-potassium ATPase. But, fortunately, we know that this is not a bullshit example, because we have, in this case, a causal proof which was done by our colleague, Professor Effort, in parallel, without us, or with us, but we helped with the compound and the separate. But independent, he could prove in this paper that by the typical staining experiments and so, that this brestine extract has, I would say, very similar activity to the very famous drug Taxol. So it can be really comparable, and this is really a big step forward, because so far everybody believed this is ATPase, which is the target. No, the main target for cancer is here. Okay, that's it. I have one final scientific slide, and this is a slide which is a little bit also my institute is a plant institute. I want to urge you to not only look at frankincense. You've heard there is more works on frankincense than on any other natural compound. If you really want to go into it, it will be quite hard. But there is so many interesting plants here which offer so many interesting possibilities, also in areas which you might not have thought of at all. Because I don't know, I mean, you're not growing a lot of potatoes in Oman, but the biggest potato disease is late blight disease, which caused the Irish famine, which is $1 billion problem. It also is a disease not only of potatoes, also of tomatoes, as you can see here on the side. So we tested some extracts, not Boswellia, other plants. I can't show you which, of course, or don't want to show you which, but you can see that some of them, even at the lower concentration here, had very nice activities against this Phytophthora infestans. Very selective. And it's something to go on further on. Yeah? So there is other possibilities, don't leave them out. There is more beyond frankincense. Thank you very much. Finally, I have to thank my co-workers, of course, the ones here in, where it is. Katrin Franke was the most important one because she did all the phytochemistry work on the nerium. Mohamed did the anti-cancer metabolomics. Robert is the screening head. Martin is the entomologist. Of course, here Luai and is good friends since more than 25 years almost, yeah. And Professor Effort, because he, and that is exceptional, he made the causal proof of our correlation analysis before we had done that even, or finished it. Okay, that's of course luck. Yes. And I would thank the colleagues of the other departments and all the co-workers which were engaged in it. And I thank you for listening. Yeah, this camel, when I was invited some years ago in King Saud University, we had a trip out, and this camel fell in love with me. It was following me all the time, putting his head on my shoulder. And when my wife came close, it made yeah. So I don't know, this camel fell in love with me. And since we also work with antibody drug conjugates, to target our very active cancer compounds, I think I should look also in camel antibody drug conjugates. Camel have very special antibodies. That might be interesting. Thank you very much for your attention.
Thank you so much, Professor, for a very nice and informative talk. Now our session. We can have one or two questions. Yes, please.
Okay, I have one question. Okay, so you propose that the difference between hot and cold extracts is the deactivation of the enzymes?
Yeah.
It's very reminiscent of my beer brewing days, because you heat the malt to activate the enzymes to cleave the sugars.
Yeah, that's true. You can activate, and we have done similar observations when we worked on certain natural dyes, which you have to heat to 70 degrees to activate the enzymes. But if you do it at 100 degrees, you denature. So it depends on the optimum curve of the enzymes, where it is and where it comes from. So yeah. And we are about to isolate the enzymes too, and then we will find out what is their temperature curve. But obviously, at the high temperature, they are dead. Yeah. Hidayat.
Yeah, I just have a short question. Yeah. First of all, thank you so much for a fascinating talk. I mean, I like the story of cold versus hot extract, so denaturation. I have, comments maybe and a question also, like you mentioned in the hot extract sometime, the chemical composition also changes, you mentioned of the enzyme also, but I saw some paper also if you heat the extract, sometimes phenolic compound, like, flavonoids, they change to monomer, even trimer also. So sometime as a nature, because in traditional medicine, some plants are suggested to heat it and then drink it. So sometime as a nature product chemist, we don't isolate those compounds which is present in the hot extract, which is maybe used as a medicine. So this is just like a comment. So.
Yeah, you're totally right. I mean, especially when you do hot extraction or very concentrated extraction, you can see chemical reactions between compounds, polymerization, oxidation, of course. You can also see, especially in hot extracts, what we see here is that we see total hydrolysis to the genins, without any sugar. But that's bad also, because in this case, in other cases, is what you want. So at the end, we solve this riddle a little bit. But on the other hand, it still is only one cornerstone to produce stable and in its concentrations of the different compounds, really reproducible extracts. Or maybe I'm too much a chemist, I would rather go for a single defined compounds, because these different constituents also have slightly different activities, some of them better, some of them worse. If I have a single compound, which I can isolate also from the extract, because synthesis would probably not make sense here, but if I have a way of having a controlled separation and a controlled enzymatic breakdown, so that I get really to a single clean compound which does the job, that's probably the entry into at least Western pharmaceutical industry. Yeah.
Thank you for your presentation, for your nice presentation. As I'll take from your last word, there is a lot of plants can be used in medicine. It's from my experience as a local citizen here in Dhofar. A lot of trees can be used as antibiotic, as gives a low temperature if you have a high temperature, and for stomach, for eyes, for different things. With the frankincense. Frankincense oil is also good for stomach, for pains, for coughs, relief from the hard coughs. It's also from the experience after Corona, with the time of Corona.
house building and the city spreading out, which is of course to some extent endangering this very, I mean, compared on the world scale, it's a small area which has this richness. So you have to really be careful to preserve it and make use of it in the proper way. But you will manage, I guess. Thank you very much. Yeah.
Thank you so much, Professor. Thank you.
One.
What is the active element that is in the frankincense that can used against cancer or like medicine?
Yeah, I said I'm not the expert in frankincense. There is others like Hidayat who can answer that better than me. Or we don't know. I would guess in these experiments with the cold extract of frankincense, because it showed so different. First of all, we have to re-verify it, that it's not some measurement error or something. So it was just a very quick result. But I would guess that it's not boswellic acid in that case, because a cold water extract would not extract a lot of boswellic acid for sure. So it must be something else. Yeah. There is always a little bit more to things than you look at. I mean, they're still finding new stuff for aspirin, for acetylsalicylic acid all the time. So it's amazing if you dig deeper how many things you find and how much we don't understand yet. Yeah.
So you mean the big two family?
Yeah, frankincense. If we got the frankincense from here, so yeah, that's the other thing. I mean, what we could really use here in the region is a good botanist and a repository of plant samples and so on, because it's to validify what you have and always sending it to Q is difficult, of course. So thank you very much for that.
Thank you, Professor. The discussion is really interesting, but we have time limits. So now it's time to invite our next keynote speaker, Professor Dr. Hans-Herbert Feibig. Professor Feibig is a renowned figure in the realm of medical oncology and hematology. Professor Feibig is the founder and CEO of 4HF Biotech. He is retired professor of medical oncology and hematology, University of Freiburg, Germany. He is founder of Oncotist GmbH. He has been awarded Krenzi Prize from German Society of Hematology and Oncology, and he has more than 350 publications. We are honored to have him join us today.
These investigations 20 years ago. working in Halle as a Humboldt stipendiat. And, he convinced me that in the traditional Arabic medicine there are clues and plants which need to be exploited. And since I was always interested in natural products, I started a big series. No? Today I have 2 lectures. In my first, I will briefly talk about the immune stimulatory effects of briastine in volunteers, and the second will be about the anti-cancer activity. Next, a short introduction. You know well, natural products from plants, microbia, are the origin of about 40% of drugs against cancer. So was a rich source discovered mainly in the last century already. Examples are the taxanes, camptothecins, anthracyclines, mitomycin C, epotilones, so a large variety with different mechanisms. And Oman has a very rich biodiversity of plants, being the origin of many remedies used in traditional medicine. Here in Oman, more than 11,000 plant species are known, and many grow here in Dhofar area. And extracts were used since more than 2,000 years in the traditional Arabic medicine, and the best examples you know very well: Boswellia sacra, Nerium oleander, Nigella, Acacia, Camifora, and so on. The background and the active ingredients are better understood today, but not fully elucidated. For instance, for frankincense. Of research of Dhofar University plays an important role in their further development. In my former company, which was called Oncotest, I investigated more than 24,000 extracts and pure compounds derived from plants originating in the Middle East, in India, and in China. And we had identified 8 leads which were also patented. And these programs were, on one hand, cooperation program sponsored by the German Ministry of Research and Technology, and the program with India was with Nicolas Piramal. in Mosul and later in Amman in Jordan. Briastin is available as a solution for intramuscular injections, but also as and I will explain you this. This here is Gerhard Kelter. He ran all the in vitro studies, so one of my best co-workers. No? And here, I don't know his name more. So here is the control. We have no release of the cytokine. So this is 0. We have here lipopolysaccharide. That's the positive control. Now come here. Here the positive control. In both very high levels were measured. This was a negative control. And here you have Briastin given in different concentrations from 0.2 microgram per milliliter up to 3. And at the higher dose, the release here of the IL-6 was almost as high as in the positive control in both donors. And with the lower concentration, accordingly, a little bit less, but still significant release. So Briastin increased the concentration of IL-6. For TNF-alpha, here it's similar. Vehicle control, no. Positive control, slight increase. Here another positive control, higher. And so Briastin really affected the high release of TNF-alpha in a concentration-dependent manner, but here from 0.5 up to 3, very high. For interleukin-1, only the highest concentration showed a release, the lower no. For IL-10, almost no release here. And for IL-2, which is the growth factor for T lymphocytes, also no effect here. And if I summarize a little bit the function, when we have a release of interleukin-6 and TNF-alpha and also interleukin-1, what happens in the different organs? In the liver, acute phase proteins are produced, and at the end it activates the complement system. In the bone marrow, the neutrophils are mobilized, and which at the end results in phagocytosis. In muscles and fat tissue, here we have decreased viral and bacterial replication and increased antigen processing. So it's clear, and also in B lymphocytes and in activation. Effect on certain critical pro-inflammatory cytokines. No? The conclusions: Breastin acts as a strong producer of IL-6, TNF-alpha, and interleukin-1. The cytokines increased with the higher doses. We did not observe an proliferation inhibit effect here at these doses, and an increase in these cytokines show that within the immune system, the monocyte macrophage systems are activated, as well as lymphocytes and NK cells. No? So as a consequence of this property, what potential applications are that could be used in patients with viral infections, but also as a concomitant anti-cancer therapy, because cancer patients have, in many cases, a weakened immune system, and also when it's given in combination, cytotoxic agents produce a transient immune suppression. And here, the stimulating effect of Breastin could be of therapeutic value. No? I will show you now a short summary about the studies being carried out against viral diseases, and these studies were supervised by Luai in different phases, so these are not my data, I report what he has observed. And he found activity in several viral diseases like HIV, against hepatitis virus B and C, also against influenza A, B, and C Hong Kong strains, and no activity was seen against herpes virus, the reovirus, and the yellow fever virus. So clearly, on clinical studies, and I will also briefly mention autoimmune diseases. virally infected cells. The second vaccine showed clinical efficacy against hepatitis B, C, HIV, influenza virus, and also against some autoimmune diseases, as I have shown. And these encouraging results make the product more appealing to be used in the treatment of a wide range of virus-induced and autoimmune disorders. So this is my presentation. I thank you for your attention.
Thank you so much, Professor Paivik, for this very nice and impressive presentation. We will have another talk from him also after the break. But now, if you have any question, please, you can ask. We have time for 1 or 2 questions. Yes, please.
Yeah, thanks for a nice talk. I have general question. I mean, I think the Bristine also show antiviral properties.
Yeah.
Yeah, so it can be used for COVID-19. I mean, some
COVID-19.
Yeah,
Uh,
they have same mechanism. I don't know.
I have no, probably yes, but I don't have data. Louis Rashan, I think he can answer this question.
Thank you.
Would be a tremendous good opportunity for.
Any other question, please? Professor, just one thing. Professor,
just a short question. If you increase the pro-inflammatory cytokines like IL-6, TNF, and IL-1, this would lead to a pro-inflammatory response. So would that mean that maybe a side effect of Bristine treatment is the increase of inflammation somewhere in the body?
Yeah, that's true. The clinical side effects with high doses are mainly fever, high fever up to 41 degrees. So it's really a reaction probably about this cytokine release. And other side effects include nausea, vomiting in about 10%. And there was another one, diarrhea also was observed in a small percentage. Otherwise well tolerated. So of course it was really observed if there are any cardiac effects, extra systole, but this was not reported. Okay.
Which is nice, but also a little bit surprising, because everybody would expect that there would be some cardiotoxicity because of the cardiac glycosides included.
Yeah.
Is it because of the preparation, that the cold water preparation could be better tolerated than hot water extracts?
Maybe, yeah. And also Professor Vesjohan, he told that the dose effective against certain cells was much lower compared to toxic effects on myocytes. No? Yeah.
In vitro is in vitro.
In vitro is in vitro, of course, and clearly with Bristine, when it's used in broad clinical applications, it must carefully be analyzed that there is no overdosing. No? And because it's clear that cardiac glycosides in higher dose can have serious effects up to cardiac arrest in the extreme case.
So if it would ever come to a clinical application, it should be avoided to be combined with anthracyclines.
Yeah. Mm-hmm.
And another note of care. Rats and mice are not very sensitive to the cardiac arrest. So you can feed them much more, and then it lures you into believing you have a large therapeutic index, which you don't have, because humans are very sensitive to it and mice are not.
And mice, they tolerated high doses, 160 milligrams per kilogram 2 days, but they showed severe clinical signs. So they were lethargic, convulsions, and with 120, that was a dose well tolerated, even after repeated injections. So this also then a steep dose response curve. From
Thank you so much, Professor Faibek. So it's now time for a break. Please join all of us for lunch and pray, and we will be back here after around 40 minutes to listen again to Professor Faibek for the next talk, inshallah. Thank you so much.
Thank you.
Hello. Thank you for coming. We've had a small change of lunch venue. It will not be in the foyer. It will be on the top floor. We will guide you, no problem. So we're currently on the second floor. The lunch will be served on the third floor.